Hello everyone and welcome to the third mathematics tutorial in this series for SE 4030 Key Skills for Chemists. This tutorial is titled Algebra 2. And what I want to do today is to continue our discussions around algebra, and in particular to develop what we were looking at the very end of the last tutorial. That is rearranging equations, and in particular rearranging equations using the BODMAS scheme. So this really should cement your abilities to learn how to rearrange equations using this BODMAS scheme. Now, we spoke last time that often in chemistry we need to rearrange somewhat complicated equations, and that these equations might have different operators. Okay, so some equations might have addition operators, subtraction operators, multiplication operators, division operators, and we can use the BODMAS scheme to help us rearrange these equations. Now, this is a really important tutorial because a lot of work that you do in physical chemistry, in the laboratory, and indeed in other areas such as analytical chemistry, comes down to the rearrangement of equations and solving for the variable that you're interested in. So the first thing we do is we identify those operators. We identify which operators are present. And secondly, we assign priorities for those operators according to the BODMAS scheme that we introduced in the last tutorial. Thirdly then, starting with the operator of lowest priority, we perform the inverse operation to both sides of the equation. The important thing here is that there's a fail-safe way to rearrange an equation. And we rank operators into a hierarchy, again, according to that BODMAS scheme, and we essentially unpick the equation bit by bit, but in a very systematic way. The order of those operators, the word BODMAS doesn't change, so the order of the operators is exactly the same whether we perform a calculation or a rearrangement. The key thing to remember here, the sole difference when rearranging an equation as opposed to performing a calculation, is that we use the BODMAS scheme backwards. So in this case, we unpick the equation from the subtraction end of the BODMAS scheme first, and we unpick the equation from the brackets end last. So let's have a look at a couple of worked examples. Again, a really, really important part of your maths and chemistry study this. So the strong magnets inside a mass spectrometer accelerate a charged ion. After a time of t, the ion's velocity has increased from u to v. The acceleration here is a, and all of those variables are interrelated according to the equation v equals u plus at. And in this worked example, we are asked to rearrange the equation to yield an expression for the acceleration a. In other words, we're asked to make a the subject of this equation. So let's have a look at that in a bit more detail. We start to unpick the equation bit by bit, and we start to look at what kinds of operators are present. The operators present in this equation are addition and multiplication. If we're working backwards in the BODMAS scheme, we know that we must unpick the equation from the addition end first. So here u is added to at, so we perform the inverse operation here and we subtract u from both sides. So we get v minus u equals u minus u plus at. Now we know that that u minus u value is equal to 0. So we can remove it from the right hand side of the equation, leaving us with v minus u equals at. Now we unpick the next operator, moving up our BODMAS hierarchy. And we know that we've got to unpick that multiplication term. So here the a term is multiplied by t. So we know that we're trying to solve for a, so we've got to divide both sides of the equation here by t. And that gives us v minus u over t equals at over t. Now, of course, we can rewrite that slightly, and we know that that t over t parameter on the right-hand side of the equation will cancel each other out, and we are left with an expression that is solved for a. So another worked example here. The value of the Gibbs function, delta G of reaction, varies quite strongly with temperature T, according to the Gibbs-Helmholtz equation that you see there. In this worked example, we are asked to write an expression in which delta G is the only term on the left-hand side of the equation. In other words, we're asked to solve for delta G or make delta G the subject of this equation. So again, we think about the kinds of operators that are present in this equation. And we note that here delta G has been divided by T. So we simply multiply both sides of the equation by T. And what we get is something that looks like that. Now we can rewrite that slightly as T over T multiplied by delta G. So we know that that T over T term will cancel each other out. And finally, we are left with an expression in which delta G is the only term on the left-hand side. Now there's a little note there about how we leave the part in brackets, the delta H over T plus C, we leave that alone. And we're treating that as something we call an indivisible whole in this equation, or a compound variable. So it appears in brackets, we don't need to touch it. We can treat it as a whole. So another worked example, the Hucker rule says that a fused ring system is aromatic if the number n of its pi electrons obeys the following equation, n equals 4n plus 2, where n is an integer such as 1, 2, or 3. And we're asked to rearrange the equation to make n the subject, lowercase n. So again, we know we've got an addition and a multiplication there. We're working backwards in the BODMAS scheme. We know we've got to deal with the addition first. So 2 has been added to 4n, so we subtract 2 from both sides. We know that that 2 plus 2 minus 2 term is going to be equal to 0, so we remove it from the right-hand side of that equation, which leaves us with n minus 2 equals 4n. Now we've got to deal with that multiplication step that's on the right-hand side of the equation. So here n has been multiplied by 4, so we divide both sides by 4. And we're left with n minus 2 over 4 equals 4n over 4. Now we know that those two 4's on the right-hand side of the equation are going to cancel each other out, and we can write to solve for n. This worked example deals with the Kirchhoff equation, which is about how the enthalpy change accompanying a reaction varies according to the temperature. And we're presented with an equation here, and we're asked to rearrange the Kirchhoff equation here to make Cp the subject. So let's think about how we're going to do that. There's quite a few variables and quite a few operators in this equation. Firstly, we're trying to solve for Cp here. So the delta H1 term is added to Cp, so we subtract it from both sides. Now we can get rid of it on the right-hand side of the equation because we know that delta H1 minus delta H1 is equal to 0. So we're then left with the equation on the bottom there. And here Cp is multiplied by T2 minus T1. Remember here the T2 minus T1 is in brackets, so we're treating this as a compound variable. So we divide both sides here by T2 minus T1. And of course, when we do that, the T2 minus T1 on the right-hand side of the equation will very simply cancel out, and we are left with an expression that is solved for CP. So here we've got the Gibbs equation, delta G equals delta H minus T delta S. And we are asked to rearrange the equation to make the change in entropy delta S the subject. So let's have a think about how we can do that. Well, we can firstly invert this subtraction step by adding T delta S to both sides. If we do that, we know that that minus T delta S plus T delta S term on the right-hand side is equal to 0. So we're left with a simpler version of that equation. Now we can see that delta G is added to T delta S, so we can subtract delta G from both sides, leaving us with T delta S equals delta H minus delta G. And finally, we can invert that multiplication step whereby delta S is multiplied by T by dividing T by both sides. And of course, if we write the equation properly, we know that on the left-hand side, that T over T value will cancel each other out, and we are left with an equation that is solved for delta S. So pause here for self-test 1. What I would like you to do here is rearrange the equations to make X the subject in each case, and the answers will follow on the next slide. So here's the first set of answers for self-test 1. And here are the second set of answers for self-test 1. Now, last time we spoke about some rearrangements involving simple powers and roots, and I'd just like to go over one more worked example about how we rearrange simple powers and roots in equations before another self-test. We know that the BODMAS scheme accommodates powers under the heading of, and you'll remember that to rearrange a power, we perform the inverse operation, right, which is generally a root. Raising anything to its nth power and taking the nth root are inverse functions. So we can write a general set of equations, a raised to the power of n equals b, so therefore a equals the nth root of b. So let's see how that might work in practice with a worked example. The dithionate ion, here represented by the Roman numerals 2, is an extremely powerful reducing agent and readily reduces organic aromatic species. The rate law when reducing with dithionate is written as rate equals K multiplied by the concentration of your aromatic species multiplied by the square root of your concentration of dithionate ions. K here is the rate constant. And in this worked example, we're asked to rearrange the equation to make the concentration of dithionate ions the subject. So if we work backwards in the BODMAS scheme, then the first thing we've got to deal with, even before we deal with the square root here, is the multiplication step. So we know that the concentration of dithionate ions is multiplied by K aromatic. So here we divide both sides by K aromatic. And of course, if we do that, then both those K aromatic terms on the right-hand side of the equation will cancel each other out, and we're left with an equation rate over K aromatic equals the square root of our dithionate ion concentration. Here our dithionate ion concentration has been square rooted, so we want to perform the inverse operation and square both sides. And of course, if we square both sides, we know we're going to free up the term on the right there, and therefore that equation is now solved for the concentration of dithionate ions. Okay, so pause here for self-test 2. Have a go at rearranging these simple roots and powers. Rearrange to make x the subject in each case, and I'll point out once more that if you're struggling with any of the content in these tutorials, then please refer to the relevant chapter in the Monk and Monroe textbook. And that will give you some extra worked examples, some extra questions in there, and the directed reading on the relevant chapter can be found in the Moodle page for this mathematics tutorial. Answers will follow on the next slide. And here are those answers for self-test 2. Okay, that's all we've got time for today. Thank you very much.